Okay, in this section, we are going to look at how, back to kind of our motion problems and how they are related to area. Okay, so here's a little example. It says a train moves along a track at a steady rate. So this time their velocity is the same the entire trip. Steady rate at 75 miles per hour from 7 a.m. until 9 a.m. And what is the total distance traveled by the train? Clearly, you can figure that out. Rate times time equals distance. So I can take 75 miles per hour times 2 hours and get 150 miles. If we think about graphing that problem, what it would kind of look like is this. Okay, my steady speed is 75 miles an hour. So this is 50, 60, 75 miles an hour would be something like that. Okay, I continue at 7 o'clock, I'm going 75 miles an hour. At 7:10, I'm going 75 miles an hour. At 7:20, I'm going 75 miles an hour. At 7:30, I'm going 75 miles an hour. So this speed stays constant the entire time. I do that every minute for 2 hours until I hit 9 o'clock. Okay, so this is kind of like the magic stopping point. I'm really measuring my time from 7 o'clock until 9 o'clock. Okay, so I'm measuring this time right here as 2 hours. And clearly my velocity the entire time is 75 miles per hour. Okay, what I could do is I could actually figure out the area of that little box right there. Again, I know that I'm going from 7 o'clock to 9 o'clock. This is 2 hours. My velocity or my y value here, or my height of my rectangle, is 75. And if I find the area inside this box, I have 75 times 2, which is 150, which of course is the distance we knew that the train went, was 150 miles. I found that by actually using area. Okay, I can use my algebraic formulas, but I can also use area to think about it geometrically. Okay, so pretty easy if an object is moving at a steady speed. But what if it doesn't? Okay, so that's how I found this, by the way. The area of space above the x-axis and below the velocity curve gives me the distance traveled. So we talked about that already. In this case, it's a rectangle. I find it by doing base times height. Since the train was going at a constant speed, it created a rectangle. Very easy to do in this case. Okay. However, what if the velocity varies? So what if the train goes 75 miles an hour for a while, and then it slows down, slows down, slows down, slows down, so it's just like coasting, and then it goes at this speed for a while. Okay. Now the area in that yellow region there that's underneath that curve um, is not a rectangle. And right now you have no way to find the area of that region. It's not a shape that you recognize. It's not a trapezoid. It's not a triangle. It's not a anything. And you have no way to find the region of it. Okay. And this is where calculus came in. They went, all right, we've got to find a way to find the area of that region. So what people did is they took an irregular region, okay, and they divided it into teeny tiny rectangles you can think about, okay? So this right here is one rectangle, if you can kind of picture it. They divided it into little tiny, tiny intervals, okay? And they basically thought about that as a rectangle. Now you can find the area of a rectangle, right? And I can find the area of each rectangle that's underneath that curve. And if I add each of those rectangles up, it should give me the area that's underneath that curve. Now, clearly, since a rectangle does not fit perfectly under a curved line, this is somewhat of an estimation. But the smaller and smaller and smaller, the thinner your intervals get and the thinner your rectangles are, the more accurately they can fit underneath that curve and the more accurately they can give you an estimation of the area that's underneath there, which of course can give you your distance traveled. Okay, so what we are going to do is we are going to kind of look at an example here. It says, consider a particle that moves along the x-axis that has a velocity right here of t squared. And it's asking what is the position of the particle at t equals 3. So it wants you to kind of know how far it moved. Okay, we are going to look at just kind of a subscript of this so that we don't have to do the whole entire problem. So we're going to just, here's a graph, t squared. Okay, this is the graph t squared from 0 seconds until 3 seconds. So we can divide that graph underneath the curve, so this area underneath here, into a whole bunch of rectangles. What we're going to focus on, just in the interest of time, is what's happening between 0 and 1 seconds underneath this curve. Okay, and then just we're going to use that same, you would repeat that process over and over and over and over again until you had all the rectangles under 3 seconds. Okay, so we're going to just zoom in on that area that's between 0 and 1 second. Okay, so what I did is I divided that area between 0 and 1 second into 4 even intervals. So this interval right here goes from 0 to 1/4. This interval right here goes from 1/4 to 2/4, which is 1/2. Okay, so on, so on, so on. What I did is I found the midpoint of this rectangle right here. I'm looking at this rectangle right here. The midpoint is the halfway point. Okay, I went up until that midpoint hit the green line or hit the curve. I measured how high it was, and I come up with a rectangle. Okay, I'm going to show you this on the next screen because I think it'll be easier to see. Oh, maybe not. Okay, so here we go. The base is 1/4. The height is the y value when x is 1/8. So again, this is what I mean. Okay, this is what I mean by that. The midpoint, I'm looking at this rectangle right in here. Okay, the midpoint of that rectangle is halfway between 0 and 1/4. Halfway between 0 and 1/4 is 1/8. I go until, so my x value is 1/8. I want to figure out what my y value is. Okay, and then the area of the rectangle would be the base of the rectangle. The base of the rectangle is 1/4 times the height, which is this distance right here. And if you can't estimate it exactly, you can certainly plug it in. The x value that I'm using is 1/8. 1/8 is halfway between 0 and 1/4, right? So I can go 1/8 and square it and get 1/64. Okay, so 1/4 times 1/64 gives me my area of that rectangle. Okay, I can move on to the next rectangle as well, and I can keep repeating this process. Okay, if I look at this rectangle right here, the base is the distance between 1/4 and 1/2, okay, which obviously is 1/4. So that's the base. The height would be this distance right here, okay? And it's at the midpoint between 1/4 and 1/2. And if you don't know what the midpoint between 1/4 and 1/2 is, it's 3/8. And if I plug 3/8 into my coordinates, so I'm plugging in an x value of 3/8, this would be 3/8 squared because that's what my function is, okay? So again, if you do that, and you can kind of estimate how this happens, but if you plug that in, your base is 1/4, your height is 3/8 squared, you get 9/64, da da da. And you keep repeating that process with every single triangle that's underneath there. Okay, you do it again with this triangle or this rectangle right here. Did I say triangle before? That rectangle. The base is 1/4. The height is however high that is. Okay, and I have it down here so you can see it. 5/8 squared, 25/64. So 1/4 times 25/64 is 25/256. Okay, you keep doing that, keep doing that, keep doing that, keep doing that for every single rectangle that's underneath that curve until you get to 3 seconds. I didn't show you all of them, okay? But here they are. And notice I have a dot, dot, dot in here because I didn't show you every single interval, but that's what it would look like. And then what you get to do, so there's all those rectangles. There's lots of rectangles. I'm adding up the area of every single rectangle under here. So I would add this answer plus this answer plus this answer plus this answer. I would add them all up. And when I add them all up, I get to be about 8.98. Okay, it says, would the area of this irregular region still give the total distance of the object traveled? Yes. Is it an estimation? Yes, because do those rectangles fit under there perfectly? No. Okay, but it is a very close estimate that the object would move 8.98 units, whatever that is, if it's miles, feet, inches, whatever, in the first 3 seconds. Okay? When you do an infinite amount of rectangles under there, okay, so the smaller and smaller and smaller your intervals are for your rectangles, the skinnier your rectangles are, the easier they can fit underneath the curve and the more accurate they're going to be. As you do more and more and more and more and more rectangles, as your rectangles approach infinity, you arrive to what is called the definite integral. Okay? And we'll talk more about the definite integral tomorrow, but I want to show you kind of a couple of examples of how to do this. So we used the midpoint rectangular approximation method. The rectangular approximation method, or RAM, is when you draw rectangles underneath. Some people use the midpoint of the rectangle to do it. Some people use the left-hand endpoint. Some people use the right-hand endpoint. And I'm just going to kind of show you kind of what happens when you use both the left and the right endpoints. Okay. So this is a curve. What I am telling you is I am telling you that n equals 6, which means I want you to divide your area underneath your curve into 6 equal intervals. Okay? Here's what I'm wanting you to do. So I'm wanting you to find the integral from 0 to 12, the area that's underneath that curve from 0 to 12. So I'm wanting you to go straight up here. This is where your 12 is. Okay, this is 10 and 8, 6. You can do this, 4, 2. I can fill all these in if I want to. I don't need to, but I could. Okay, and if I were doing the midpoint, okay, if I were doing the midpoint, here's what I would do. Obviously, this red first rectangle is your midpoint. If I want to divide it into 6 equal rectangles, you can see that the base of each rectangle is going to be 2, just so you know. If you were doing the midpoint, what I would do is I would take the midpoint of that region, I would draw a line straight up until I hit the curve, and then I would make a rectangle out of that point. So it would look something like this, okay? And I would go here and straight up until I hit the curve, and I would make a rectangle out of that point. And I go here, straight up till I hit the curve. Okay, and you can kind of see what's shaking down. You can continue that process. That's if you do the midpoint, okay? If you do the left side, what you do, still the same intervals, okay? From the left side, it would look like this. I take the left side of the interval till I hit the curve, go straight across, make my rectangle. Ooh, that was really crooked. Okay, let me fix that just a little bit. Straight up till I hit the curve. Again, this is my next part of my interval. Okay, so I go and I take the left side of it till I hit the curve, and I make a rectangle. Okay, left side of it till I hit the curve, make a rectangle. And you can kind of see what happens. Clearly, this is not nearly as accurate of an estimation. Okay, and then there's the right side where you take the right edge of each interval. So here I would take the right edge, go up till I hit the curve, make a rectangle. Right edge till I hit the curve, go up, make a rectangle. Okay, and you can figure out the base and the height of that as you go. So we're going to actually do this with a function here that I'm going to give you. The function is x squared plus 2. And I'm telling you, I want you to find the area underneath that curve from 0 to 6. I don't know if we're talking about time right now, but from 0 to 6. And I want you to break it into 6 sub-intervals. Okay, so I want you to draw the graph, and it kind of gives you the directions right here. This time I want you to use left RAM, right RAM, and then we're going to average them to do midpoint. Okay, so here we go. First of all, we're going to do this with our right ram. Okay, so I'm only going to go from 0 to 6 seconds. So I'm really wanting to find the area under the curve from here to here. Okay, that area in there is what I'm wanting to find the area of. Okay, I need to divide it from 0 to 6 seconds into 6 intervals. So clearly each one is going to be um, one interval long. Okay, first of all, we're going to do it with right ram. If I do it with right ram, here's my first interval. I'm going to go up till the right side of my curve hits the graph. Okay, make a rectangle, and it looks something like this. My base is 1. It looks like my height is probably 3. So I'm going to say that that rectangle right there has an area of 3. Okay, I go until the next one hits the right side. So right side, hit the curve, go over, make a rectangle. Base is 1, height looks like it's 6. Okay, 1 times 6 is obviously 6. Okay, keep repeating this process. So here, right side, hit the curve, go over. Okay, my base is 1. My height right about here looks like it's about 11. 1 times 11 is 11. Oops, sorry, not 16, 11. Okay, I'm going to let you hit pause and keep doing that, and you might estimate that a little bit differently than I would. Okay, but when I estimate it, I got 103 about. Okay, your number might be just a little bit off, but I would add 3 plus 6 plus 16 plus da da da. And again, it might be a little bit off. I got about 103. Yours might be a little different than mine. I would keep repeating it all the way until I got, this will be the last rectangle that I would do right here at 6. Okay, and my right side has to hit 6. Keep going, estimate. Okay, so again, I got 103. All right, then we're going to do it again with the left side and just show you how different these numbers can be. Okay, same intervals. I'm going from 0 to 6, but I'm choosing to do the left side. So this time I'm going to go until my left side of my interval hits the curve, go across, make a rectangle. It looks like it's about 1 by 2, which is 2. Okay, left side has to hit the curve, go across, boom. It looks like it's about 1 by 3, so that's 3. Okay, I'll do one more. Left side hits the curve, go over. This one looks like it's 1 by 6, which is 6. Okay, again, you can estimate all of those, and yours may be slightly different than mine. The last rectangle that I would do would be the one that goes right here till I hit the curve and over, just so you know. Okay, that will be the last rectangle that I would do. When I did this, I got it to be about 67 when I added 2 plus 3 plus 6 plus all the way to the last rectangle. Okay. Then this next one is asking us to find the mid-ram. Okay. And first of all, you know what? I'm going to do this. Clearly, this number is 67. When we did the left ram, or sorry, the right ram, we got 103. Very, very, very different numbers, okay? The right ram or the left ram, either one, depending on which direction the curve goes. But one is going to very much overestimate the area under the curve, and one of them is going to underestimate the area under the curve. If I find the average of the mid ram and the right ram, it should give me a very different answer, okay? If I find the average between those two, if I average 67 plus, I'm going to just do this up here, my average was 67 plus 103, and I divide that by 2, I get 85, okay? That was my average. Now, I'm going to compare that to what I get when I do my midpoint RAM. When you do your midpoint RAM, Again, you just take the halfway point of each rectangle and you go up. So I go up here, hit the curve, rectangle, okay? And it looks like it's about 1 by about 2, so I'm going to call that 2. Go up at the midpoint till I hit the curve, make a rectangle, and it looks like it's 1 by 4, which is 4. Go up at the midpoint till you hit the curve. Okay, estimate, it looks like that's about 8. Okay, keep going, 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 going. When I add all of those up, I get 82. Okay, and those rectangles are much closer to what the average of the left and the right side are. Pretty close when I average them and I do the midpoint. So the midpoint is definitely the most accurate one to do. The left RAM and the right RAM will over and underestimate, but the midpoint RAM is the most accurate. Obviously, the smaller your rectangles are, the more accurate your estimate is. Okay, smaller intervals give you more accurate of an estimate. Okay, and that'll do it for this lesson.